Vanakkam. Welcome to this video on biomechanics. We have been looking at kinematics of grasping and reaching. In the previous videos, we looked at 2-link serial kinematic chains and 3-link serial kinematic chains. In this video, we will be looking at a more generalized notation for n-link serial kinematic chain. What would be a method that you would use to compute the endpoint coordinates when there are n links with different linked links? The popularly used method in the field called as DH parameters, Denavit-Hartenberg parameters, also called as DH parameters. As it is in the 2-link chain and the 3-link chain, we saw that the forward kinematics itself becomes complicated after some point. The inverse kinematics is a little too complicated. Unless you have some assumptions, you really cannot even solve for the inverse kinematics. Either there must be some constraint or there must be some. This constraint can be a geometrical constraint, this constraint can be a physical geometrical constraint that a particular link cannot go beyond a particular point, or this constraint can be such that movement in a particular joint is somehow linked to movement in a different joint. That kind of some constraints you need to have to be able to uniquely identify or uniquely solve for the inverse kinematics equation. And this complexity keeps on increasing as the number of links proceed. We saw that in the previous case, because 2-link kinematic chain we solved, that was not too bad, it was relatively easy. The moment we jumped to 3-link, suddenly the complexity jumped. And as the number of links keep on increasing, the complexity keeps on increasing. So, also so far we have assumed only planar kinematic chains, but then real world robots and real world humans can make movements that are not in a plane. Right now the movement that I am making is in space, is in 3D, right. Technically you can solve for these, technically you can still use trigonometry and first principles to solve for this, but it will be a little too tedious, a little too difficult to solve, right. So, we are in a situation where we need to use some analytical method, some generalized analytical method to solve for these both forward kinematics and inverse kinematics, right. So, this was first suggested by Denavit and Hartenberg in 1955. So, Denavit and Hartenberg used some standard notations, right, some specific notations that are always followed using their method, right. These are, every joint is represented by a coordinate frame. There is a coordinate frame that is placed at every joint, every single joint, and this is such that, and this coordinate frame is placed such that the z axis is always the joint axis. The z axis of the joint is always the joint axis. This is how it is placed by definition. For example, if the joint is a revolute joint, then z axis will be along the direction of the axis about which the joint rotates, right. Or if it is a prismatic joint, then the z axis will be along the axis about which the joint translates. So, by using these methods, by using this simple approach, a manipulator, a multi-link manipulator becomes a whole bunch of set of coordinate frames, right. Only coordinate frames are there in this. The links alone, how do you define the links? The links are defined by the relative position and orientation of their frames, of the coordinate frames, right. So, the shape of the link is eliminated. What kind of link this is, that is eliminated. This approach is called the DH parameters or the Dynavit-Hartenberg convention. And this consists of 4 parameters in total, 2 joint parameters and 2 link parameters. 2 joint parameters and 2 link parameters are used in DH convention. Right. And what is the notation? Links are always from 0 to n, and the 0th link is the fixed link or the ground. Joints are always from 1 to n. Right. So, the ith joint is between links I minus 1 and I. Remember, so remember that link starts from 0 whereas joint starts from 1. So, that means that the first joint is between the 0th link and the first link. Okay. Something to keep in mind. Consider these 2 links I minus 1 and I, and there are 3 joints that are involved. These are joint I minus 1, joint I, and joint I plus 1. Okay. These are connecting the 2 links, link I minus 1 and link I. The z axis is always along the joint. We mentioned this previously, that the z axis is always along the joint axis. Right. The ground is also shown in the figure, right, as shown, the fixed link, 0th link is also shown. Now, the question is how to find, the x axis, right, and how to find the y axis. Z axis is relatively easy to define because that is the joint axis. How do you find the x axis? That is the question, right. So, it turns out that you define the x axis as the common normal between the z minus 1 axis and the z axis, right. The x I minus 1 axis is defined as the common normal between the z I minus 1 axis and the z I axis. Okay. So, this is the z I minus 1 unit vector and this is the z I unit vector. Now, the question is what is x I minus 1, right. That has to be, because this is a plane, that has to be the unit vector because this is space, that is that vector that makes an angle of 90 degrees with both the z I minus 1 axis and the z I axis. That particular common, and there will only be one of them. So, that particular common normal is the x I minus 1 axis. This is it. Now, the point of intersection of the x I minus 1 axis with the z I minus 1 axis. The point of intersection of the z I minus 1 axis and the x I minus 1 axis is the origin of the I minus 1 coordinate frame, is the origin of the I minus 1 coordinate frame. Okay. Now, how will you find the y I minus 1 axis? That is the origin, but you still have to find the y axis. You use the right hand thumb rule, because you know the z axis, you know the x axis, find the y axis, right. Use the right hand thumb rule to find the y I minus 1 axis. Right. Likewise, repeat this process for z I, and remember, for the case of z I, you will have to do it for x I axis, that is the x I axis is the normal between z I and z I plus 1, between these two, and so on and so forth. Repeat this process, then find y I axis, then find z I plus 1, then find x I plus 1, then find y I plus 1, so on and so forth. This repetitively, iteratively you will have to keep doing. This is the framework. That it looks a little complicated, but with some practice and with some understanding, we will be able to catch with this. So, this is just the description. Right. Now, what are the 4 DH parameters defined? One is alpha I minus 1, this is the angle between z I minus 1 axis and z I axis about the x I minus 1 axis. Okay. This is that angle, that is alpha I minus 1, this is called as the link twist angle. Then link length a I minus 1, this is the distance between z I minus 1 and z I axis along the x I minus 1 axis. Remember, that is not this link length, rather this distance. Okay. Something to keep in mind, that the link length is the length along the x I minus 1 axis, right, distance between the two axes z I minus 1 and z I along the x I minus 1 axis, that is called link length. And then there are 2 joint parameters, joint offset di, which is the distance between x I minus 1 and x I along the z I axis. So, this is the z I axis, this is the z I axis, the distance between the x I minus 1 axis and the x I axis along the z I axis, that is this distance. That is that is that distance, right. This is called as the joint offset di. Right. Then joint angle theta I, this is the angle between x I minus 1 axis, this is that, and x I axis, that is that, about the z I axis, right, that about that axis, that is theta I minus 1. So, once you define the joint parameters and the link parameters for all the joints and for all the links in the manipulator, then you can construct what is called as a Denavit-Hartenberg table or the DH table, that contains n rows corresponding to n links and 4 columns. What are the 4 columns? Link twist angle, link length, joint offset and joint angle, these 4. Then you can use this DH table to find the forward kinematics equation and then solve for them. To do this, we construct the what is called as a homogeneous transformation matrix T, that is a 4 by 4 matrix. This is found by multiplying 4 individual matrices, which are essentially 2 rotation matrices corresponding to alpha I minus 1 and theta I, 2 joint rotations, and 2 translations corresponding to a I minus 1 and dA. There are only 4 parameters, right. 2 are angular parameters and 2 are distance parameters. So, that this is done. Why are we doing this? Because the frame I minus 1 is transformed to frame I, right. There is a transformation that is happening for the frame I minus 1 to I, and so on and so forth. In future, we will be discussing a bit more detail in about rotation matrices. We will be discussing more details about rotation matrices in future videos. For now, let us just say that this 4 by 4 homogeneous transformation matrix is obtained by using 2 angular parameters and 2 distance parameters, right. Now, what would this transformation matrix look like? This is how it will look like. This is the transformation between I minus 1 and I. How do I know this? Because that is the notation. It says T subscript I minus 1 superscript I is the transformation between the I minus 1th frame and the ith frame. In this, I have this 3 by 3 square matrix, This 3 by 3 square matrix is the one that is giving an idea about the overall rotation that is happening, the total rotation, not individual rotations, the total rotation that is happening, because there are two rotations that are happening, one involving theta I, the other involving alpha I minus 1. There are two rotations that are happening. This 3 by 3 matrix gives me the, or gives me a sense of the total rotation that is happening. Okay. This column gives me a sense of the translation that is happening, and I have added the last row 0 0 0 1 just to make the whole transformation matrix square. Otherwise this is a there are only 3 rows and 4 columns. To make it square, we have added the 4th row. So once again, this transformation matrix T is transformation of link I with respect to the link I minus 1, I minus 1 to I, right. And this 3 by 3 matrix is a rotation matrix, we will see more details in future, indicates the total orientation change, the total change in orientation. This is the position vector 3 by 1 vector, which indicates the change in distances or the positions. Okay. Now forward kinematics essentially is used to find position and orientation of the end effector. I am not interested in knowing the individual link parameters in a multi-link chain. I am interested in knowing the endpoint coordinates, right, position and orientation of the end effector with respect to the base, with respect to the ground, with respect to the fixed link. If there is a serial chain with n plus 1 links, I am interested in finding this T0 to n, which is the transformation of the nth link with respect to the 0th link. That would mean that there are many matrix multiplications that I will have to perform. Homogeneous transformation matrices like the one that we saw in the previous slide, they will have to be multiplied in sequence to obtain the transformations. So therefore you will have this T0n as T01 plus T12, sorry, T01 times T12 times T23 times etc. Tn minus 1 to n. Remember, the multiplication is done in this direction, right. The multiplication is done in this direction. So these transformation matrices are multiplied on the left hand side, right. So to obtain the last T matrix to the 0th, or that is the last T matrix on the nth frame to the T matrix on the 0th frame, right. If I perform it in the other direction, for example, it will not give me the correct result. Why? Because matrix multiplication is not commutative. I will not get the same result, right. So we must be very cautious about how we apply these transformation matrices. So in this video, we saw a generalized notation for studying an n-link serial kinematic chain and Danavitt-Hartenberg convention, or the Danavitt-Hartenberg parameters for defining and understanding the endpoint coordinates, or in the forward case, in the forward kinematics case, for describing a transformation matrix. Thank you very much for your attention.